So the topic of this video is to talk about the layers of the Earth and the composition of the Earth before we dive into our different types of plate boundaries. So if we were to think about the Earth, here's the Earth as a whole, and if we were to imagine taking a slice out of the Earth and blowing that up, and have a pie slice view of the Earth where this is the surface and this is the very center of the Earth. So there's a couple things to note. We have two different ways that we can classify layers inside of the Earth. The first you're probably familiar with. The outermost layer of the Earth is called the crust. And then we have this large voluminous layer beneath the crust, just below that line, called the mantle. And deeper inside we have the core. Crust, mantle, and core. Let's actually talk about each one of these. So if we were to blow up the section of the Earth right here, and we were to enlarge it so that we could see some differences, the first thing that we would note is that there are actually two different types of crust. So that's a cross-section view that I have just drawn. And we have continental, I'm just going to type CC, or write CC, continental crust and oceanic crust. And if I were to add some color in here, I could add in sea level, and so you can see that the vast majority of the oceans are above oceanic crust, although there are some of these small segments right here of continental crust that are flooded by sea level. So the seas kind of encroach and flood the outer edges of continental crust, or in other words, the continents. So what can we say about each one of these? Let's start by talking about the continental crust. First, we know that the continental crust has a granitic composition. A granitic composition. So in chapter 3, you learned about a rock called granite. Granite is defined as having a felsic composition and a coarse grain or phaneritic texture. And although there are a lot of different types of rocks within continental crust, if you were to average the chemical composition of all of the different types of crust in the continental crust, it would have the composition similar to granite. And so therefore, as we have already learned about granite, iron and magnesium are present. There are some mafic minerals in granite, but there's few. So I have a little less than sign here, FeMg, for iron and magnesium respectively. So there's not a lot of iron and magnesium within continental crust. We know that the continental crust averages about 35 kilometers in thickness, so from top to bottom. Although it gets up to 70 kilometers, so I have a less than 70 kilometers. Some of the thickest crust underneath large mountains like the Himalayas, the crust gets thicker because the crust gets deeper in these areas. And in these areas, the crust can get up to about 70 kilometers in thickness. And continental crust can be pretty old. Of course, it can be really young, but continental crust is no older than 4.0 GA. That big G that I just wrote stands for giga, and the little a stands for annum. And so this big G little a refers to billions of years ago that the oldest continental crust, not all of the continental crust, but the oldest continental crust that we've found is only approximately 4 billion years old and younger. That's quite a bit different than oceanic crust, which has a basaltic composition. So basalt is another igneous rock that you learned about. It was rich in iron and magnesium bearing minerals, or mafic minerals. So MgFe bearing. There's more of that, so I'm going to do a greater than sign right there. The thickness, as our little drawing indicated, is remarkably different. The thickness of the oceanic crust is only about 7 kilometers. So 1/5 of the thickness. And the oldest oceanic crust is only 180 million years old. This big M, little a, stands for mega annum. And the quick way to just verbally communicate this is 180 million years ago. Oceanic crust ranges as well from being brand new, just formed yesterday, to up to 180 million years old. So we don't have any oceanic crust older than that. The mantle now, contrary to what visual depictions in science videos try to depict, the mantle is solid rock. 100% solid, just as hard as the table that I am sitting at, just as solid as that. Over very long geologic timescales, the mantle can flow like a fluid. However, in the moment, the mantle is solid rock. It consists primarily of iron, magnesium, silicon, and oxygen. Those are the main chemical elements in the mantle. And its density is approximately 3 to 4 grams per cubic centimeter. Water has a density of 1 gram per cubic centimeter, so it's 3 to 4 times the density of water. I should mention the densities here: 2.7 grams per centimeters cubed and 3.0 grams per centimeters cubed. The density between these two is going to be important whenever we talk about plate tectonic processes. The core now is actually nickel, primarily nickel and iron. There's a little bit of other stuff in there, but it's primarily nickel and iron. And its density is much higher, 11 grams per centimeters cubed. So you have the crust, the mantle, and the core, their respective positions. If you were to look in the book, the surface, the boundary separating the mantle and the core, is somewhere around 2790 kilometers. But if you just remember an easier number to memorize, 3,000 kilometers. If you were to see something very close to 3,000 kilometers on a multiple choice exam, you would know it. So that's a trick that you can use to simplify some values that you might come across, not just in this class and other classes, in order to do some basic back of the envelope calculations. So I mentioned that we have 2 different types of layers within the Earth. Each one of these different layers that I've mentioned so far, crust, mantle, and core, are separated by a chemical distinction. There's a chemical change between the three different types. There's a chemical change between the two different types of crust, and the crust is notably different than the chemical composition of the mantle down here. And we can actually see this in seismic or earthquake studies. The boundary, the bottom boundary of the crust kind of sticks out within seismic data, and it's a very distinct, sharp boundary called the MOHO. This is actually a shortened phrase for a much longer term, the Mohorovičić discontinuity. I just noticed you can't see some of the stuff down there. So core, nickel, and iron. I'm using a selfie stick, so maybe I can... There we go. Bought a selfie stick just for this class. So the crust, the mantle, and the core are all different in terms of chemical composition. And that's how we can define the layers one way. The other way that we can define the layers is through assessing strength. So how strong are each one of the layers? One of the easy ways, let me use a different color. Let's use green. One of the first ways that we can show this is through identifying two different layers within the core. There's an outer core. Can't really see that. I'm gonna have to go back to black or blue. Or an inner core. The outer core is liquid, and the inner core is solid. The outer core is the only truly liquid layer inside of the Earth. Sure, there are pockets of magma, but even magma is not completely liquid. There's solids, etc. But the outer core is the only truly liquid layer within the Earth. And the inner core is solid. We should go ahead and note that this interface, this change from solid inner core to liquid outer core, is responsible for Earth's magnetic field. So whenever you have a compass and the needle points north, the reason for that has to do with the fact that we have a liquid outer core and a solid inner core. There are different layers within the mantle. We're not going to go through most of them. We can just collectively call these the lower mantle until we get further up, and we have two distinct layers. Let me draw them in here. We have an asthenosphere. And I want to be very explicit and labeling the layer that's above the asthenosphere right here. That's called the lithosphere. So these two spheres are important with respect to plate tectonics, the point of chapter 5. The lithosphere is the strong, rigid outer layer of the Earth. It has crust and mantle included within it. The crust, as well as the uppermost mantle, is included in the lithosphere. The layer directly below that is the asthenosphere, and this is a very weak layer. It's not molten, it's not liquid, but it's weak. It can deform like silly putty. And the asthenosphere is the layer that the lithosphere slides around on. The boundary between both of these is approximately 100 kilometers depth. And those are the different layers of the Earth. And we're going to be talking a lot about the lithosphere and the asthenosphere, continental and oceanic crust in future videos.